Hello and welcome to my talk on the ATTiny85 2-button debounce. You may recall, if you've seen my previous video, that we had problems debouncing a button and the state seemed to go on and off without our wanting it to. So what we're going to do today is we're going to build ourselves a little module with an ATTiny85 that will actually do the debouncing for us. Now you could do that on your microchip, obviously, on your microcontroller, but I kind of like the idea of these ATTiny85s. I saw a guy make a sine wave out of these like really small PIC controllers, and I thought, well, you know, we should try and get some more use out of these ATTiny85s. So this is the final setup. And like I say, to motivate us, we want to end up with a module like this, basically, so we can click buttons. It will flow through the ATTiny85, and the debounce buttons are there. So it's just a simple module. But that's why we're going how are we going to do it? Well, we're going to use the idea of an integrator, kind of like a Schmidt trigger, you could call it that. What we're going to do is we're going to take samples from the buttons every 3 milliseconds and count up the number of ups and downs. What you see, we have a variable which we start off as all ones. This is 8-bit wide, and periodically every 3 microseconds we're going to read a pin, both pins, and if it's high we'll shift in a 1, if it's low we'll shift in a 0. So here's typically how it might work. Start off in this state, we do a left shift on the variable, and suppose the button is low, we put a 0 in there, so the state goes from 1 1, all the ones, to 0 at the end. And then the button might go high, so we shift in a 1 like that, so you can see everything's being shifted to the left. And then maybe it's low again, so we shift all this to the left 1 and add the 0 on the end. And likewise, if it's 0 again, we shift everything to the left. You keep doing that. The variable that we store, our integrator variable, will either go 0 when the switch is depressed for 24 milliseconds, and will go high when it's released for 24 milliseconds. So that's how it works. Limitations. Now you might say there are 6 available pins on the ATTiny85. Why are we only trying to do 2-button debounces rather than 3? Well, the answer is that pin B5, which is this pin, is the reset button. Now I did have an idea. So one pin is eliminated, you can't really use it as an input or output. So you go from basically 3 pins that you can debounce to only 2. Now you can do things like burning the fuse so that it acts as a normal GPIO pin, but I didn't fancy that, because once you've burnt the fuse, you can't reprogram the chip without a lot of faff, and I didn't want to get involved with that. One idea I did have, which may or may not work, is there are 5 GPIO pins, excluding this reset pin, and of course the ground and VCC. And the idea was to switch GPIO pins between an input pin and an output pin. I'm not sure if that will work. That would need to take some consideration. So basically what you do is you read the pin. If you think it's changed state, then you turn it to an output pin and set it low, and select the reverse for when it goes high. One of the problems that I foresee is you can't just flip a pin between input and output. You either have to make it a tri-state floating pin first, or an output high. So it's floating here, but it should say output. So that might work. So you might get to debounce 5 pins. You might have to experiment with that though. So we've got this circuit set up here. What the hell's going on? Let's just show a schematic. Right, so here's the pin. There you got PB5. It's the reset pin. Voltage in, ground. You've got 2 push button switches going into PB3 and PB4 there, and how if I turn it the other way around, I'm just going to screen upside down, so something like that. So you've got the 2 button switches here, and you've got the outputs which are sent to LEDs. So PB3 essentially connects to PB2 and PB4 to PB1. So these are the debounced outputs here. Okay, this is the connected diagram. Right, here's the code that does that. I'm going to be a little bit unorthodox here in doing a lot of instructions in once. I thought about this and I thought, well, I could do it, you know, the straightforward way, but I thought, you know, does it really hurt to simplify this? So okay, so here's what we do. We've got our main function, and we're going to set our pins 4, 3, 2, 1 and 0. We're going to make pins 2 and 1 outputs. So actually, if I bring up the diagram again. So pins PB1 and PB2 are outputs. That's the DDRB is the data direction register B. And now in the next section you can see that the pins are supposed to line up here. Now we set 4 1s and a 0 here. This is a binary, of course. So PB4, which is here, we have a 1 position here. So 0 here, 0 in DDRB means it's output. If I put it to 1 in port B, that means it's an input pull-up. And we'll do the same with pin 3. It's also pull-up, input pull-up. And for PB1 and PB2, we set them equal to 1, which is output high. The default for all this is floating inputs. Okay, so now we've got the situation where PB3 is an input pull-up, PB4 is an input pull-up, PB2 is an output high at the moment, and PB1 is high, set to high initially. Okay, so these are our integrators. I've called GREAT that I discussed in the previous slide, and I've set it to all 1s, which is FF. Okay, so now we're going to loop, and people might not like this, they might like 4 loops, but I figured, what the hell, why not go for a go-to? So it's simple enough. What we're going to do is we're going to call a function called debounce, which does the bouncing. It takes parameter PB3 as an input, an output pin PB2, and the integrator. So PB3 connects to PB2 via an integrator, and we do the other pin PB4 connecting to PB1 via this integrator. Then we delay 3 milliseconds and repeat the whole thing. This is the debounce function itself. So you can got the input pin, the output pin, and a pointer to the integrator which we want to alter. So what do? We move the integrator, shift it 1 bit to the left, and then in this line we work out whether our input is 1 or 0. Is it high or is it low? That's what that does. Right. Then, if our integrator gets the full value, we turn that output on. If the integrator goes to 0, we turn the output pin off. So that's 33 lines of code. I think I have to go here. Let's just show you what the whole thing looks like. So we set our CPU speed, import a few libraries. Here's the debounce function, and here's the main function. Just scroll down a little bit. There. So 33 lines of code. Right. So that's the basics.